One, one, 1, 2. Can you hear me? One. One.
Hello.
Can you
Can you-
speak? Any questions about upcoming things, midterms, reading week, web work? No? Anybody from the chat, do you have a question? Can you hear me? Do you have any question from the chat? I'm not sure if I can. All right, good. Okay, thank you. All right. Fine, let's go. So, like I said, material stops at the inverse, but it will mostly be linear maps, linear independence. What else was it? Some dimension computations. The direct sum, the sum, and then all the examples. So make sure you go through like your matrices, your polynomials, right? So you will see a little bit of linear maps, but really we won't go further like than last week. I go. Yeah, I was just saying like, so linear independence, linear span, what else? Oh yeah, right, vector spaces, subspaces. But yeah, a little bit of linear maps, maybe a little bit of inverse. Think of it as like a Gaussian, like it drops like this, like very little of linear maps, and linear independence, linear span, all that stuff, vector space, subspace. But of course, know your linear maps, so be able to, and also, oh yeah, injective, subjective. There's some questions about it. Yes, I remember. So make sure you know your subjective, injective stuff. Okay. All right, everybody's happy. Let's go on. Yes, coordinate maps. So we've seen before that you can have a vector like this and V, but you see, we've been spoiled, right? We always think that there's only one type of basis. This is namely the 0, 1, 1, 0. And you just do this dotted thing and you get your coordinates, right? So A, B. But I could have drawn my axis, like a slanted way, like this. This is still a basis. This is still the same V, like geometrically, like in the real world. V is at the same place. I just moved around my grid. But then my components change. The vector didn't change. The components did. So then we write V of the new basis, beta, is A prime, B prime. It's still the same V, like, I wish I had a way to draw it to tell you that it's the same guy. Yeah, I should do it here, something like this. Yeah, it's the same vector in like this, but you just change your measuring system. Okay. All right, so questions? All right. So that's the idea. And when we write little e, we mean V in the Cartesian. So 0, 1, 1, 0. Okay, and you have this vector, 8 minus 4, 1. So this is in 3D. So 0, 0, 1, 1, 1, 0, and 0, 1, 0. And but you could have another basis, beta. So call this beta basis. And I will spare you the computation, but what you do is you can write the standard basis. So which way do I want it? Anyway, so you have this point, 8 minus 4. So this is 8 E1, 4 E2, plus 1 E3. then you want some expressions of B1 in terms of B1. So I even have them. So what am I saying here? I'm saying 251. So let's see. Right, so the claim is, let's see. Yeah, so V, let me do it this way. V is equal to this, and V is equal also to 2 V1, 5 E2, and 1 E3. Wow, it's B's. B2, B3. Same vector, two representations. So you can check yourself that you can go from here to here and vice versa. Is that okay? Like, is it hard? Okay, let me try it. So this guy is, let me do this guy. So it's 2 times 101 plus 5 times 1 minus 1, 0, plus 1 minus 1 minus 1. Now I have to add them all together. So I have 2 plus 5 plus 1 and what else? Yeah, 2 plus 5 plus 1, then minus 5 plus 1, and then 2 minus 1. So the first guy gives you 8 minus 4 and 1. Okay? This is the, so you can go back and forth. All right. Questions? No questions. Anyways, then I mean, yeah, this is like the main thing for vectors, and we're saying that you can do the same for linear maps. So if you give, so we'll talk about it, but remember we talked about having a matrix representation, and this guy here is called the standard representation, where you evaluate EI in terms of AIJ of the other ones, for J here. So that gives you sort of all these entries become the matrix representation. It's called the standard matrix representation. We'll come back to it. Don't worry. But then you might want some different representations, like write me AA, or maybe write me when T goes between two subspaces. I mean, two different vector spaces, alpha, beta. So the world is vast. Okay. One object we will need to do all this trickery is called coordinate maps. So why do we need this? Because you can't really formulate matrices over arbitrary vector spaces. So, for example, right, P2F, P2R, these are polynomials. 2x squared. How would you have a matrix act on this, right? Like, you know how matrices act, can be multiplied with vectors. They give you another vector, right? Right? But how will they, I might as well call it the T. But how does this even happen? It doesn't make sense. You cannot act with the matrix on a polynomial or a matrix on a sine function. Right? It makes no sense. But there is a map that takes you from these polynomials to, in this case, R3. And then you act on that. And then you come back. And you will get a polynomial. And then you come back and you get A tilde, A1 tilde x plus A2 tilde x squared. So this is the effect of a matrix multiplying polynomial. It gives you some other polynomial, but you have to go through array to do. That's it. That's the entire next 2 weeks. We're just going to prove fancy theorems about this and ways to compute it. Okay. I don't see a question. Yeah, what's the definition? So you start with some space, you have a basis, and all it does is it acts on the basis elements. So you give me some element X, it will just extract the coefficients. So for example, gamma B1 gets sent to the standard basis, so 1, 0, 0. Okay. So you always map to the standard basis. That's the target because it's the easiest. You can change it, but then call it something else. Don't call it coordinate map. Coordinate map sends you to the standard basis. Okay, questions? Right, so these coordinate maps are nice because they are invertible. So remember what I did? I went from polynomials to R3, and then I have to come back. So you need an inverse. And we proved that if the dimensions match, so dimension of P2 R is 3, which is the dimension of R3. So there exists a coordinate map, gamma, whatever your standard basis is, put 1x squared. So gamma B going from P2 to R3 and back. Okay, so we built this map last week, and the way we built it, I think I have it here. So, I mean, it's the one I just mentioned. So we just we simply took BI to EI. That was the dimension of V. That was our map. And then we built arbitrary elements like Hushan said. You just define it as the linear combination of the BIs. So CK. All right, question? I mean, I went through this, so but let me review it. It's good. So why is this coordinate map linear? Yeah, too many details. So let me clean this up. So we want to show that the map is linear. We can do it together. So you have gamma X and then Y. And then this, you can write it as C XK BK and plus YK BK. So let's factor this out. So it's CXK plus YK all times BK. All right, so now let me ask you, what is this equal to? What's the definition of the, yeah. You said plus? So, but what should I write here? You're saying I should write this or what? Yeah, exactly. So, yeah, exactly. So this is gamma, by definition, this is equal to this. Pictorially, it's like CX1 plus Y1, CXN plus YN. And you use component, vector component addition. So then this splits into CX1, xn by 1 yn, and then you undo everything. So you get c of x plus gamma y. Stuff like that. Okay. Questions? All right. So that's why you have linearity. So for injectivity, there's two ways to do this. Either you go by x not y and you prove gamma x is not y, or you do the contrapositive. You assume they're equal and then you prove that they're equal as well. So did I have a question here? Okay, I will do it. Fine. So yeah, I mean, you represent your x and your y. You plug it in. You know the definition. So well, I'm doing the general thing. Sure. So then, oh, there's an equal here missing. Okay. It's confusing. So let me rewrite this. You have gamma of x is equal gamma of this linear combination. By definition, this is equal to summation of ak gamma vk. So yeah, let's write ek here. And then same thing for gamma y, which we assume they're equal. So you have bk, ek. But ek are an Li basis. So you get ak is equal to bk for k1 to n, which gives you that x is y. All right. Yeah, okay, I answered my own question. Now let's do something together. I mean, boring. So what about surjectivity? How will I prove surjective? What's your idea? Just like whatever. So just to see if you remember the definitions, all that stuff. What's the strategy? Yeah, go ahead if you have some. Oh yeah, perfect. Yeah. Yes. Yeah. So then what do we do? So what's the proof? Do you know? Yeah, you just do regularity. So you have, what's the statement? Dimension of the image of gamma is equal to dimension of image of gamma plus 0, which is dimension of image of gamma plus dimension of kernel of gamma, which by rank nullity, it's dimension of the domain V. But we know that dimension of V is equal to dimension of W. So then, and then we also know the following result that that C was going to put in the test, but I stopped. I'm like, this is in the book. like we've done this. We all done this. Okay, sir. But she might put it in. So when V is so for V subset W, you have that V is W if and only if dimension of V is dimension of W. So, and then we have that image of T is inside W. So if you show that the dimensions are equal, then you have the same space. That's why it's a different notation. Call it U. It's confusing. And take U to be image of T. Okay? So yeah, all you needed was rank nullity. I think it's in the book as well, right? But because I don't want you writing this every time. This is boring. Someone can check. I don't remember. I think this is done in the book, but you can check. Okay. I don't see any questions. Right. Let's go on. I did it by hand. You know. Let's play with it. Right. So here's my vector space. I take R2 by I equip it with a different basis. So I equip it with the E2, E1. Okay. So I take gamma of E2 to what? What does gamma of E2 map to? What's your guess? The ordering matters. So if we write it like this, yeah. Oh yeah, this is the gamma B. So whatever the, but you always map to the standard basis. So where should that go? Yeah. Yeah, exactly. So it will go to 1, 0, so E1. And gamma B of E1 will get mapped to the other one. So ordering matters. Okay. I should ask you in the chat as well. Right, so then what am I doing here? Oh, I'm computing. Yeah, whatever. So, oh, I see what I'm doing. Yes. Okay, fine. Why am I writing gamma E here? Oh, I see, I see. Okay, let me do this one first that we just talked about. So gamma B of 2E1 plus 4E2. Your map is linear, so this is 2 gamma B E1 and then 4 gamma B E2. And now this is 2 times E2, 4 times E1. So then you have 2 times 0, 1 plus 4 times 1, 0, which gives you 4, 2. Okay. And but you could also do it in the standard basis. But then you just map. So gamma of E means that EI goes to EI. So this is like the simplest possible map you can map. You just do nothing, just the identity map. So yeah, gamma of E is actually the identity over Rn. So yeah, this is times 2E1, 42, which gives you 2, 4. Okay? So ordering matters. That's the lesson of this example. If we write E2, E1, we mean send this to E1 and send this to E2. If we write B1, B2, whatever, E1, E2, E3. So yeah, we always make sure we write it in ordered way. Right. Yeah, so I want to find gamma B. So it means I take gamma B of 1 and I have to map it as a linear combination of, so this is not really coordinate map. I don't know why I call it like this. Oh, no, I see what I'm doing. So, oh, I see. Yeah, so I want to take gamma B1 and I want to send it to the standard basis. So let me remind you, gamma B of A0 plus A1 x plus A2 x squared. This is the vector A0, A1, A2. Okay. Yeah, what is gamma B of 1? Yeah, okay, good. So I'm not going to ask the other ones. Okay, people in the chat, can you tell me what is gamma b of 1 plus x squared? Because you're very quiet, it's scary. Can you tell me what gamma b of 1 plus x squared maps to? One zero one. Right, perfect. Thank you. All right, so I think I have them all here, right? Oh, I did. So let me write them. So, gamma b of 1 plus x. Okay, let me just do the example. Doesn't matter. So now they ask you to find the gamma b of p of x. And yeah, so if you do it in the standard basis, you just have the usual thing. So 1 plus 2x squared. This is just 102. That's not right. So do I do it here? Yeah. So for gamma d, it's a little bit harder. So remember, your gamma, the input of gamma is the vector space equipped with the basis d. It just cannot add on d comma b. You have to put it in as b or as d. Whatever it takes, it has to be in the form of d. Okay, so this guy here is in the form of 1e. By e1, I mean, let me write it this way: b1, b2, b3. So this is 1b1, 0b2, and 2b3. You need to write it in d1, d2, d3. That's how you can then put it in gamma d. So this is just calculus. So I had to do some subtractions. I mean, we can go over them if you want, but the idea is you can try to match this side to this. So I did that, and I get that this is 1d1 minus 1d2 and 2 times d3. Okay? Is that okay? Now you can put it in. So do I do it here? Okay. So gamma d of p, in this form, it makes no sense. Because remember, gamma d of di is ei, but I don't know what gamma d of, what is it, bi is. I don't know. You have to write it in terms of the b's, of the d's. I have no idea. So here you write it as 1d1 minus 1d2 and 2 times d3. So you get 1 minus 1, 2. So remember, gamma b of p is 1. Let me do it here. So this is not 102, which is gamma b of the same polynomial. So the moment you change the basis, you change the coordinate map, you change the output. So gamma b is not gamma d. They have different outputs of the same polynomial. All right. So that's the tricky part of this, that you always have to be careful with the input. Okay. Right. Yeah, that's the main scary part. Okay. Yeah. All right. So we've talked about changing representation for vectors. Now we want to figure out with linear maps. So the one you've learned so far is T in the standard basis. Now we can explore all the other ones. So here we can explore T of B, D. So the goal of this week is to understand this diagram. So you will be given some linear map. Like let's say this is P2 and this is P1 and T is the derivative map, right? This is a linear map, but how do you define matrix for the derivative? Doesn't make any sense. So remember, right? D of A0, A1x, A2x squared is defined as A1 plus 2A2x. So matrix makes no sense. But we will find a way to express the derivative as a matrix because it's a linear map. And that's all you need. All right. Yeah, we will explain all this stuff. So it's not. So yeah, so the diagram basically says you give me something complicated like derivative. I will give you some other map called a D bar, which will be between vectors. And this guy has a matrix representation. So when you take some x from here, it will be some matrix x. So this D bar, see right in the notes, acts as matrices. D is not a matrix, but you map it to something that has a matrix representation. So D bar for derivative will be, how do I say it? Gamma D derivative map gamma B. So we're going to use our coordinate maps to write down the matrix. So this will be the most abstract part of this course. And we'll go very slow and repeat it multiple times. Okay. So that's the benefit. You gave me some crazy linear map. This map T bar has a one-to-one correspondence with matrices. So you give me any map, let's say Rn to Rn, there's a one-to-one correspondence with matrices. Rn to Rn. Right? So it takes a vector and give you some vector. So you can always associate a vector to this T bar maps. Okay. All right. And I think I did the example here. Okay, yeah, let's do an example. The derivative one. Then we'll do all the proof stuff. So again, derivative is it takes nth degree and it maps it to n minus 1. So let's go here. So it takes a0 and xn. So this is 2 times n an xn minus 1. So that's the mapping, and the question is, can you represent this as a matrix? So this is a bit too much, so let's keep it cleaner. Let's just do P2. This is easier. So it takes a0, a1x, a2x squared, sends it to a1 plus 2a2x. All right. Can someone tell me, yeah, here or in the chat, what does gamma B map this to? Just the first one. So what does it map to? What's the image of gamma B, the coordinate map? Here or in the chat, can you tell me? What should I put in the components? Yes. What about this guy? But in what order? So what do I put first? Huh? Can you speak up? Sorry. And then, yeah, so, right, so there's no, yeah, so that's the tricky part. There's no zero because this is the coordinate map of P1. So I should have maybe written in a different way if that confuses you, like maybe gamma tilde or something. So this is just A1 to A2. Is that confusing? Maybe I should write gamma tilde because P2 has the coordinate map that goes to, in general, right? Pn gets mapped to Rn plus 1. So this should go to R3, and this guy goes to R2. That's all. Okay. Right, so now let's find the matrix. So we define T bar to be this gamma. So I even forgot. Gamma B. So let me put tilde here. If that doesn't matter. Okay. So right, I want to find the matrix. So gamma B tilde goes from P1 to R2. Its inverse goes from R2 to P1. So let me ask you, can somebody tell me what's the domain and the image of this map? Let's start slow. What does it act on? What's the input of this matrix? This should be R3. What am I writing here? Yeah, this should be like this. So yes, so this guy takes R3. It maps it to, so yeah, let me split this out. So first of all, yeah, it goes from, yeah, it goes from R3 to R2. So that's the answer. But let me explain why. So this guy takes R3 to P3, P2. This is gamma B inverse. Derivative takes you to P1. And gamma tilde takes you to R2. So this R2 gamma B. Is that okay? So that's why those are 3 to R2. So you need a matrix. So this T bar acts on A0, A1, A2, and it outputs what we said before, A1 to A2. So that's what you need. You need a matrix that does this. Okay. Right. So how do you figure this out? Oh yeah, let me ask you. I have the answer. So how do you figure out this matrix? So here or in the chat, how can I? So now we can forget everything else. We just want a matrix that does this. How can we find this matrix? Yes. Yeah. Good. Oh, you okay? Yeah. Go ahead. You have more. Yeah. Exactly. So, right. Perfect. So, yeah. Let me go with my It's too much. Let me call it. So yeah, so you need 100 to get mapped to the origin. You need what else? 010 to get mapped to 10. And let me put T bar here. And then 001 to get mapped to 02. And let me make sure I have this right. Yeah. So I have to act on A0 and 1 and 2. So yeah, let me do it step by step. So how many columns should I have? Since I act on R3. I know it's obvious. I just, yeah. Three columns and how many rows? Two rows. So, and indeed, I have 3 of them, and I evaluate the. So this will become my these are my columns. Okay, these 3. So you put 0, 0, 1, 0, and 0, 2. That's your matrix. Okay, let's check it. So you multiply it, then you get 0, 1, 0. So you have 0 plus A1 plus 0, and then 0 plus 0 plus 2A2, which is exactly what we requested. That's it. So that's how you find that's the entire process. I'm gonna do this many times. Okay, questions? Right. So then, okay, I'm proving the one-to-one correspondence. All right, good. So I'm proving that if you give me any T bar, I can do what I just did. I can give you a matrix. So there's one-to-one correspondence. So I call it S here, but in our mind, we mean this T bar map. And sorry, what was your first name? Yeah. Sukar? Sakura. So like Sakura said, all you have to do is evaluate at the basis. So, and this will give you the columns of your matrix. So then, okay, I go, so this is A1, I should put J. Where's my matrix? Yeah. So my matrix will be, let me write it in big form. It will be A1, 1, A, N, J, 1. So this is the SE1. Then SE2 is what? A 1, 2, A and 2. And then my SEN is A1 and ANN. So all you have to do is evaluate your map on the standard basis for your field. In most cases, we'll just do RM. And then you put them as columns. So this will be the matrix. So given a map, we can give you a matrix. So we have to do the converse as well. But that's how you get the matrix, which is what you care about in practice. Right, so suppose you start with the matrix. And we've talked about this a little bit. So again, this is AJ. Keep forgetting. So you define your map on the basis. Okay. So you define it as A, what is it? N, J, oh no, I call it K. For J1 to M. of EK. So this will be your map. And the lesson is you can always build a linear map by just defining it on the basis. So let me ask you again. This is the third time I asked the same question, but it's a good question. How should I define T of X? I know, just keep it going. What should the definition of T of X be? Here or in the chart? So what do you know? You know your map on the basis. So how should we define it in general? What? Yeah. Right. So what should I write here? So if X is I don't know, like CKEK, what should my image be? Yeah. Yeah, and then, so I mean, that right away is good enough, but it will be the double sum. So you have K, J, CK, and then A, what do I want? J, M, E. I should use what do I have here? I have too many Ks. Let me call this L. So this is L, 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 and then this is K. K, J. What is going? So many stupid. Oh, this is K. Oh, and this is L. All right. Now I understand. Now I see it. Okay. And the first one actually goes up to N. Okay, let me like break this down. So you have the input, you have N columns, okay, and you have M rows. And an entry over here will be of the form AL all the way to AML. All right. So, but yeah, don't write these double sums. You will get it's too confusing. Just write what the part said. Just write summation of CL times TEL. That's like simplest of all. So don't kill yourself over this. All right. Yeah, so that's how we get it for all V. Just define it coefficient wise. Okay, so that's it, right? We got for every T bar, there's a matrix. And this T bar, we did the derivative map. You computed using this coordinate maps. And this is the representation. And then, yeah, that's it. Tomorrow we'll talk about potential basis. Thank you.
Professor, hi. I just had a quick question. So C, to my knowledge, hello?
Yeah. Yep. I have a
For the J thing, for the EJ,
yeah.
just for EJ, not the vector, that should be just summation from 1 to n of AI, right?
I wrote something else.
I think.
Yeah, no, but what you wrote is correct. So it would be the
If
J.
it's J,
Yeah, if it's the J, it's the column. Yeah. That's right. Yeah.
And you can just use this for now. So T of T of EJ,
Sorry, can you repeat?
so the existing over T of EJ, so we can use the double on there. Because so there's just going to be like, so okay, I'm using T1, T1, of that,
What are you? No, no, I'm kind of confused. So if you're
The
talking
idea
about the matrix representation, you just have to do what you just told me, which is
so we don't need to define it on the vector. We can define it on the basis.
yeah,
The
you
matrix
only
vector
that's
of
right.
the-
Yeah, yeah.
Okay.
But the hard part is I mean for the derivative example, like you don't know how it acts on the standard basis. So you have to use the coordinate map.
So, Professor, do you mind if I ask a question? Hello, Professor? Oh, I guess not.